So thank you for being here. We're halfway this summer school. It's starting to get dense and we're probably all a little bit tired, but we'll try to get through this together. I thank the scientific committee with Olivia Caramello and Laurent Laforgue and Alain Cohn for this invitation to talk about, as Olivia correctly said, the Quantaloid enriched categories for sheaf theory, let's say. So I'd like to explain essentially a result due to Bob Walters, who is an Australian, so he was an expert in enriched categories, but who is also a professor for many years here in Subria, I think, not very far from this place, so it's a nice coincidence. The starting point, let me just mention this as an introduction. The starting point is really the definition itself of a sheaf on a locale. So let me just say, to make it perfectly clear, that a locale or a frame or a complete Hating algebra is a complete lattice in which we take very often the supremum as, I write the supremum as a big V, so a join. As a complete lattice, it also has infima, but it's the finite infima which will be important. And in fact, there is also a top element in the locale, which I'll write as T. And the defining property of a locale, so it's a complete lattice with all these, say, operations if you want, but the defining property is that finite meets distribute over infinite joins. So something like this. All right, so a locale being a poset, it is also a category, a posetal category. You take its elements as objects and you write exactly one arrow when you have the order relation which is satisfied. And therefore, it makes perfect sense to talk about pre-sheaves, contravariant pre-sheaves on such a locale. So because the locale is viewed as a posetal category, this functor, if you wish, takes a very simple form. It will send every element of your locale, I'll use more traditional letters maybe, U for an element of the locale, it will send it to a set of what we call then sections at U, or elements of level U of the pre-sheaf for the moment F. And whenever V is smaller than U, because the pre-sheaf is contravariant, there will also be a set of elements at level V, and there will be a mapping from FU to FV, and a unique one, because there is only one arrow, if you wish, from V to U in L. And so instead of giving complicated names, what we do is we write this as a restriction. When you have an element X of F at level U, you like to write this unique mapping into, well, X is defined over U. You want to define it over a smaller element of L. So we think of this as a restriction. So of course, all these notations, all this terminology reflects what we do with topological spaces, of course. Because the prime example of a locale is indeed the opens of a topological space, and this, say, more or less abstract definition is precisely then the topological definition. But it's not yet a sheaf, it's simply a pre-sheaf. So when do we call this a sheaf? It's when it has the gluing property. So of course, this is all extremely explicit, what I'm doing, just to get the notations right. So when do we speak of a sheaf? Well, when you have a compatible family, so when you have a covering of an element in the locale. So simply saying that one element is the join of a bunch of other elements. If you give a whole bunch of sections at the UI, but not any old section. These sections need to be compatible. These elements need to be compatible. So what do we mean by this? Well, if I take another, so I need to take a complete family. If I take two of these elements, say an xi and an xj, then because I'm in a locale, I can compute the intersection of ui and uj, which is obviously both smaller than ui and it's smaller than uj. So there is a restriction in this sense, in the functorial sense, of xj to this intersection. There is a restriction of xi to this intersection, and what we simply ask is that these two restrictions coincide, are the same. So that's a compatible family. So whenever you have such a compatible family, the sheaf condition or the gluing condition is precisely saying that there exists for every covering and every compatible family a unique gluing, that's to say, a unique element on level U, which restricts to every member of this compatible family. So that's the definition of a sheaf on a locale. Okay, now these sheaves are the objects of a localic topos, and as morphisms we simply take natural transformations between the pre-sheaves. Okay, so this is probably right after you study sheaves on a topological space. This is probably the example that you will study for a topos. It's a localic topos by definition. Now, we always hear that the toposes behave as categories of sets, and we can try to make this really explicit because, well, it's a continuous family of sets, but you can take, why not? You can take the coproduct of this continuous family of sets. Right? So what we do is just we make one big gigantic set and we put all these local sections of the sheaf in this gigantic set. Okay? Now obviously we have these elements in this coproduct, so this joint union of sets. We have these elements and we can try to compare these elements, but clearly if we take some x on level U and we maybe take some y on level V, so they are both elements of this gigantic set of sections. We'd like to compare these two elements, x and y. Now, if they are defined over different levels, for example, then obviously they are different because they live in different components of the coproduct. So if I ask you, is x equal to y, then the Boolean answer to this question is very often no, simply because, well, maybe they're not even defined over the same level. But the Boolean answer to this question, the yes-no answer, is not the interesting answer. The more interesting answer to this question is to say, okay, so we have an element x which is defined, say, on an open on level U. We have another element defined on a level V. Could there not be a common part on which these two elements coincide? So what I mean is we have U, we have V. Could there not be a W smaller than both U and V, such that if I take my x and I restrict it to W, if I take my y and I restrict it to W with my functor, could it not be the case that at some smaller level these two elements do coincide? That's to say, their restrictions coincide, right? And that's now the more intelligent answer to the question, is x equal to y? The yes-no answer is not very helpful. But what is helpful, what turns out to be very helpful, is to see this as a truth value in L. So the answer will not be 0, 1. The answer will be an element of L. Right? So technically speaking, what should I do? What am I saying? I'm looking at all levels below U and V, so below their conjunction, where I want x restricted to this lower level to coincide with y. Now there may be very many of these, but luckily I'm in a quantile, so I can take a join. And I compute a single element in my locale, which answers the question, is x equal to y? It's not 0, 1, it's the largest open set, if you wish, on which the restrictions coincide. Okay? Now this makes this object, this sheaf, it turns it into some kind of multi-valued logic object, some generalized object logic. So it turns it into a set equipped with an L-valued equality. And an obvious question now is, can we do sheaf theory with this description in terms of, say, generators and relations instead of the functorial description? So is there a way to understand sheaf theory, maybe for localic sheaves, maybe more general, in terms of sets equipped with a, say, many-valued logical equality relation? And the answer is yes. So it was proved with several formalisms from the 70s on by Higgs and by Foreman and Scott. But I think that Bob Walters gave really the nicest answer to this question, because he employed enriched category theory. Right. So that's my problem. Can we do sheaf theory with a many-valued equality? And the answer turns out to be yes. And in establishing this answer, we will also establish links to other subjects. Okay. So, in fact, to treat this question nicely, I want to talk first about a slightly more general concept than locale, which is quantile, and in fact we will move even to quantaloids. Okay, so I'll try not to forget something. So as you can see, a locale is given by a complete lattice, and there is this structural relation which relates intersection with suprema. The definition of a quantile is really, quantile, the word was invented in the 80s as a contraction of quantum locale, quantum in the sense of non-commutative. So a quantile is really more or less the same ingredients. You take a complete lattice, Q, it's written Q, a complete lattice for which the supremum is considered as the primitive operation. But now we replace intersection, which is indeed, in fact, associative, and for which the top is indeed the unit. We replace intersection and top by an arbitrary multiplication and unit. So we take a complete lattice, which is also a monoid, just a plain old monoid, associative unital, and we require the same structural equation, except that now, because I don't ask my multiplication to be commutative, I have to ask it both ways. So okay, so it's just the non-commutative version of the above definition. It's what we call a quantile.
Multiplication is associative.
Yes, it's a monoid, so it's associative and unital. It's a real monoid. So it's a complete lattice. It has two structures, complete lattice and monoid structure, and they are compatible in the obvious way. Okay? So it's a very simple mathematical object, and it appears in a lot of places. But perhaps for us, its single most important property for these notes or these lectures is the following trivial observation. If I fix an argument in my multiplication and I send every b to a times b, I'm just saying that this map preserves joins. It's a join preserving map between complete lattices, and therefore it has an adjoint as an order preserving map. So the same holds for the other guy. If I fix my second argument, clearly I'm just stating that multiplying by b is a join preserving map, and join preserving maps between complete lattices have adjoints, right adjoints, as order preserving maps. So there are adjoints to these two maps, and they are called residuations. Now, very many notations exist. I'll write them with a down arrow like that. And there is a good reason for that, I think. It's because, in fact, you can think of these guys as implications. So A implies something, and something is implied by B. Because you have, so you think of the multiplication as generalizing conjunction, and then the residuation to conjunction is implication. Right? So why do we think of this as an implication? Well, because you can write the following thing. It's completely equivalent. You have A and quote, B being smaller than C. If and only if A is smaller than C, which is implied by B. If and only if B is smaller than A implies C. It's the defining property of these two adjunctions. So when I state these adjunctions, I'm really just stating that such an element exists, and it can be computed explicitly as a supremum. But note that it also means, because we have units and co-units when you have adjunctions, it also means that A times A implies B is smaller than B. And similarly, A implied by B times B is smaller than A. So if you read this as A and A implies B is smaller than B, then you have a modus ponens. But you have both ways, because the thing is non-commutative. So this very observation, trivial as it may be, is somehow enforcing the idea that the quantile can serve as truth values for some kind of logic. Its elements are truth values. Instead of 0, 1, it's a whole bunch of truth values, intermediate values, and so on. We think of supremum as some sort of infinite conjunction. We think of multiplication as some conjunction. And we have, well, two implications, from left to right and from right to left, with their respective modus ponens. Okay. Now, let me quickly go over a couple of examples without too much detail. Obviously, a locale is an example of a quantile. In fact, algebraically, it's nice to see that so a quantile such that every element is smaller than 1 and is idempotent, so is equal to its own square, is precisely a locale. Okay, so that's an example. So locales are very, very nice quantiles, commutative ones. Another example that you can easily check, and is important, is when you take all relations on a set. When you take all relations on a set, these compose, but you can also take unions of relations. Happens that this is a quantile, non-commutative. Let me see which other examples could be interesting for the rest of the talk. Here is a very important one, sometimes called Lauvier's real numbers. You take positive real numbers and you add infinity. Now, the little trick is to view this as it is a complete lattice, of course, but instead of taking joins as primitive, we'll take meets. So it is as if we turn around the order relation. Okay? Then it happens that if you take sum and 0, then you have a quantile again. A very special one, very nice one. It's commutative because plus, ordinary sum of real numbers is commutative. In fact, it's also what we call integral because its largest element is 0 because we've turned around the order, right? So I should probably write something like this here. Opposite order to the natural order. So 0 is the biggest element, and it's also the neutral element, so it's what we call an integral quantile. And it has very many other very nice properties. In fact, this guy, something that you can easily see, is isomorphic to another guy that you probably also are happy to accept as an example. If I send a real to e to the minus x, then I will turn 0 infinity into the interval 0, 1, this time with a normal order. Order turns around by this map. Then infimum becomes supremum, plus becomes times, and 0 becomes 1. As quantiles, these things are completely isomorphic. Lauvier preferred this one. We'll see later why. But you can reason perfectly well with this quantile as well. So it's another perfect example. And it's an example that actually generalizes in a very significant way. So people are interested in a subject which is called fuzzy logic or many-valued logic. People are interested in very particular quantiles as object of truth values, very particular ones. They call these guys, they call them continuous T-norms. They call them continuous T-norms. But these guys turn out to be exactly quantile structures on 0, 1. So 0, 1 with its lattice structure. We want the number 1 to be the unit of the quantile, but we allow other multiplications. We allow other possible multiplications. Right? Now, it's not any old quantile structure on 0, 1 which is integral. It has to be what is called divisible. And divisible means that these modus ponens, which is an inequality, saturates to a particular equality. Namely, we want this guy to satisfy the following two equations. Okay, so what is continuous about these T-norms? Well, it has been proven that these quantiles are precisely given by a multiplication which is a continuous function. And moreover, such a continuous multiplication is always commutative. So these continuous T-norms are specific quantiles which are important for people working in fuzzy logic. Okay, so there are many more examples. I'll skip a few, but we can, of course, discuss. There is a beautiful classification of these continuous T-norms, which goes back to a theorem from the 50s from Mostert and Shields, which basically say that there are only 3 possible continuous T-norms. Namely, you can take product, like in the isomorphic copy of the Liouville quantile. You can take intersection, so it becomes a locale. And you can take what is called Lukasiewicz multiplication. And basically, any other continuous T-norm is an amalgamation of these 3. A clever way of putting these 3 together. Right? And so these are really the logical objects for what is called basic logic. It's one of those substructural logics. So it's a lot of words, but it's a very important type of quantile in a field called fuzzy logic. Okay. Now, the title also mentions, or Olivia also mentioned, that I want to talk about quantaloids. And when there is an oid somewhere in category theory, then you think of groups and groupoids. So you think of a kind of many-object generalization of the thing we have at hand. Now, very obviously, we have a monoid, which is also a complete lattice. So what I'm going to describe is a category, which is, in a suitable way, also a complete lattice. Right? Now, for those who are used to this kind of stuff, what am I saying? What is this definition of quantile? One other way of phrasing it in a very sort of highbrow way is saying that it's a monoid object in the symmetric monoidal closed category of sublattices. So what I'm actually simply going to do is state the definition of a category enriched in sup instead of a monoid in sup. But I'm going to do it in an elementary way because I think it's more appropriate in a lecture course. Okay. So second definition, Quantaloid. So use your groupoid intuition, or monoid category intuition if you wish. A Quantaloid Q is a category such that, so where am I going to put these complete lattices? Such that every Hom is a complete lattice. And I'll take the joins again as primitive. And what am I going to say for these two equations? I'm simply going to ask that composition in my category distributes over local joins. So these are called local joins because they happen only in Hom sets. Every Hom set is a Hom lattice, complete lattice. I'm taking join as primitive. And I'm asking composition in the category to distribute over local joins. So what I'm saying is that if I now have a bunch of arrows like this, say a whole bunch of GIs, in every such situation, so there's a whole bunch of parallel arrows that I call GI. What I want is that H after the join of the GIs is the join of H after the GIs. Now it's composition in my category, right? So, and I also want the other way around, so the join of GIs after F should be the join of GIs after F. So it's the same thing, except that now my monoid has been turned into a category. But apart from that, we still have residuation. And it now just takes the following shape. If you have an F, a G, and an H, 3 arrows with compatible domain and codomain, then G after F is smaller than H, if and only if, so by the same adjunction argument, but now on Hom sets, on Hom lattices, there will exist a unique arrow. So let me get it right. H is implied by F, and there will be a unique arrow. G implies H. Right? So we can still do logic, we can still think, but now of the arrows of the quantaloid as truth values, we can think of the composition of these arrows as a conjunction which by geometrical nature cannot be commutative. We exclude commutativity, but we still have these implication operators. But now they act on arrows, but mind, if I want to write H implied by F, they have to share the domain, and if I want to write G implied H, they have to share the codomain. Otherwise, it doesn't make sense. Okay. Now, again, there are certainly examples that we can note. Obviously, a quantale is a one-object quantaloid, right? So Quantaloid theory is really enlarging quantile theory. Instead of taking relations on a single set, I can take all sets and all relations. All sets and all relations. It's a quantaloid because it's a category, that's for sure, for relational composition. And given fixing two sets x and y, looking at all relations between x and y, I can simply take unions. And this will provide my suprema, local suprema. So that's certainly a quantaloid. The mother of all quantaloids is actually, literally, the category of complete lattices and submorphisms, because I told you that the quantaloid is actually a category enriched in this guy. Okay. Right? There are also, well, again, many other examples. There are free quantaloids, there are quotient quantaloids, there's a way of computing a lot of stuff. But for us today, what is important is that very often quantaloids appear naturally when you do universal constructions on quantiles. So very often when you manipulate... right, so the reason for introducing these quantaloids is because we have many examples, but for these lectures, because they... I shouldn't have done this. But because they arise naturally when we execute certain universal constructions. Now I'll be light on the precise expression of these universal properties. I'll just give you the concrete constructions that I'm interested in. So I'll just explain. There are many interesting examples, but I'll explain two. So one is something that Peter Fried says, always split your idempotence, right? So there is what is called a split idempotent completion. which is meaningful for any category and has very good properties, but I'll just indicate it for quantaloids or quantiles. If Q is any quantaloid, we'll invent a new one, we'll build a new one, which I'll call Q sub Si for split idempotent. So if I invent a new quantaloid, I'll have to tell you about its objects and its arrows. And of course, the local suprema, composition law, and so on. Now, it's something that you may have seen already for categories. So as objects in this new quantaloid built from the old one, we'll take idempotents. So endomaps that are equal to their square. Nothing more than that. As arrows in this category, if I have two such idempotents, I have to give a definition of an arrow from x to y. So I have an idempotent E on x, an idempotent F on y. Well, I'll say that, say, T is an arrow from E to F. When it is an arrow from x to y in my original quantaloid, the given quantaloid, but I'll ask compatibility with the idempotents. So, such that F after T is T after E. All right? So the objects are idempotents. Given two idempotents, I declare an arrow to be an arrow in my original quantaloid from the domain of the first idempotent to the domain of the second idempotent, but it has to be compatible in a precise way with these idempotents. Okay? So local suprema are computed as in my original quantaloid. And composition is done precisely, take the same composition as in your original quantaloid. And identities are interesting. The identity on an idempotent is the idempotent itself. So, to write it with painstaking detail, the idempotent is itself the identity on itself. Okay? So we can split idempotents, and note that even if I start with a quantile may have very many idempotents. There are at least two, 0 and the top element, and the unit element as well. But there may be many, many more. So even when I start with a quantile, splitting idempotents will produce a quantaloid. Okay? Here's a second universal construction that will be very meaningful for us. There is another very important universal construction, and it is, say direct sum completion. And it relates to something that Alain Kohn was talking about yesterday, very important remark, that rings we all love, but rigs, semi-rings without negatives, are also beautiful objects. And a quantile is a semi-ring. It's a semi-ring, it's a complete semi-ring if you wish, because we can take the join as sum and the multiplication as multiplication. So it's a semi-ring, but it's a complete one because we can take infinite joins, infinite sums. So all sums converge. But why do they converge? Because they are idempotent. So they are complete idempotent semi-rings. Now, as it was remarked by Alain Kohn yesterday, when you see semi-rings, in fact, you can take any handbook on ring theory and try to do whatever you can do without negatives. And one of the things that you can surely do is matrix calculus. And so there is a new quantaloid built from an old one, from a given one, in which the arrows will be matrices. So this is how it goes. You take any quantaloid, Q, And we're going to transform it into something that you could write as Q plus, because in fact we are going to add infinite direct sums. So again, there is an analogy with ring theory. In ring theory, we know that we can take finite sums, we can take finite products, and they coincide. And there is even a very nice equational presentation of these direct sums. Quantaloids and quantals are very much like rings, except that, the intuition being that we replace finite sums by infinite suprema. And so many of these results that we know from ring theory will work for Quantaloid theory, and we can even do infinitary stuff, because my sums are infinite. So what I'm going to do is, it's also written like this. I'm going to define a new quantaloid, which actually is the universal completion for direct sums, infinite direct sums. But I'm going to give you a very concrete description. So I have to give you the list of objects. So what is an object in this new quantaloid built from the old one? It has to be some kind of indexing set for matrices. So what does it look like? It is what we call a Q0 type set. Q0 is my notation for the objects of Q, right? So what is such a Q0 type set? It's just a set, X, with a function that I'll simply write as T, that assigns to every element of your set, X, a type, that's to say an object in Q. Okay? I have to give you the arrows of this category, and these will be matrices. So they are Q1 matrices. So matrices whose elements will be arrows of Q. Right? So let me very explicitly write this. A matrix M from X to Y will be, so what is a matrix? A matrix is just assigning, it's a big rectangle, typically with a number of columns, a number of lines, and for every index for a column and a line, you have to assign an element. So I'm going to write this down, and my indexing sets will be X and Y. So it's just writing for every element in Y and every element in X. So my notation is contravariant because we compose from right to left. It's assigning an arrow. It's assigning an arrow in Q. So it means that for every yx, there will be some kind of, there will be an element in position yx. It's going to be an arrow in Q, but I want it to be an arrow from the type of X to the type of Y. So my notation is contravariant. Watch out. Okay, so it's a matrix. It's a gigantic matrix. It's indexed. It has lines and columns, if you wish. And in position X, Y, there is an arrow with appropriate domain and codomain. Okay? Now I have to give you a composition law. Get away with it. Okay. So now I have to give you a composition law, and in fact it's matrix composition. So if I have to give you a composition law, I can take a matrix M from X to Y, N from Y to Z, and I want to compute N after M. Right? So I have to compute, what is a matrix? I have to compute for any little x in big X and any little z in big Z, an element of this composite matrix. Right? Now what do I know? I know that M has elements, M goes from X to Y. M has elements, with an X in this position and some Y in the other position. N has elements with a Y in so from indexed by Z, Z and Y. And I asked MYX to be an arrow from the type of X to the type of Y. NZY is going from the type of Y to the type of Z. So these are two arrows that compose. And I can do this for all Ys, take a join, and this is matrix multiplication. You see? So the formalism is really matrix multiplication. So this is a join over all Ys in Y. And these joins exist because they're indexed by a set. Everything is compatible. All domains and codomains are compatible by good choice. Okay, so that's the composite. There are local supremas. Local suprema of two matrices is just element-wise. Or a bunch of matrices, even a whole family of matrices, is just element-wise. And what is missing? Identities. So the identity matrix on a set, so what is the identity matrix in linear algebra? It's 0 everywhere and it's 1 on the diagonal. You do the same thing. You write identity arrows on the diagonal and 0 arrows everywhere else. What's a 0 arrow? It's a supremum of the empty set in the home. Okay, so, well, I'm not going to write this, so maybe I have to invent a, so the identity matrix from X to X has some kind of Kronecker delta as elements. So it's 0 if, and it's 1 on the type of X if X equals X prime. So it's the 0 in the Hom Tx prime Tx. So these things exist because these zeros are empty joins and the ones are identity arrows in Q. Okay, so this is a new quantaloid built from an old one, and even if I start with a quantile, this is a quantaloid. So they are unavoidable once you start to do, say, linear algebra a little bit. Right. Because they are quantaloids, they are also residuated. That's an important point. So to say that they are quantaloids is not just saying, well, of course, it's just verifying the definition and checking that all the conditions hold, and it's not very difficult, but it implies that it has the whole structure of a quantaloid, in particular residuations. So we can compute very logically in these gigantic new quantaloids built from given quantiles or quantaloids. Okay, now to finish this first section, I have to say a little word about commutativity. So we've seen locales, which are very special quantiles, and they're commutative. The multiplication is commutative. We've seen examples of quantiles, notably these continuous t-norms on the interval 0, 1. And for example, product on 0, 1 is also commutative. So certain quantiles have the good idea of being commutative. For a quantaloid, this doesn't make sense to speak of a commutative quantaloid because, you can't say that G after F is the same as F after G for any F and G. Domain and codomain would not match. But there is a way out. There's an extra structure that you can add to your quantaloid, or that is present in your quantaloid, that sort of allows for a study of symmetry, at least, and that's an involution. So I'll be needing this. So an involution on Q is, so an involution on Q, which I'll typically write as, say, the association. So the fact that you can associate to any arrow in your quantaloid an arrow that goes in the opposite direction but has, so it's turning around arrows, like it's an involutive algebra, if you wish. But of course, we have to ask some compatibility. So it has to be a functor from Q up to Q, so it's functorial. It has to be order preserving. So in fact, it means that it is join preserving. So that's the involute of a join of arrows is a join of the involutes, right? So okay, and it has to be involutive. So that means that doing it twice gives you back the original arrow, right? So for a quantile, so the example, how do we recover commutativity from involution? Well, for a quantile, is commutative if and only if the identity is involute, is an involution. So you have a trivial involution. Trivial involution means commutative. So in that sense, being involutive, having an involution, is generalizing this. Okay. So I think I'm slower than I thought I would be, but that's always the case. But perhaps it's, well, I still have a couple of minutes before a break, 5 minutes perhaps. So I can now introduce end this first lecture with a definition. Of a Quantaloid enriched category. So that will be the main object for the rest. So I'll talk about Q categories and functors. So here's the definition. It's really the definition. So a Quantaloid can be seen as a bicategory. And Benabou, when he defined bicategories, also defined categories enriched over a bicategory. And I'm going to state his definition, but let's say simplified to the situation at hand and with a notation which is slightly more modern. Because he didn't call them enriched categories, he called them polyads, because they generalize monads in a sense. But here's how I'm going to treat them. So take any small, just to be on the safe side, small Quantaloid, then a Q category, which I'll write as a C, like a B, C with this notation, is to give a set of objects, but it's going to be a set C0, which I think of as the objects of my Q category. Types, so it has to be a type set. So I have to give you a function from the objects of this category to the object of the Quantaloid. So every object is associated, has its own type in the Quantaloid. So a set of objects, types, and HOMs. So what is the HOM going to be? For any two objects, I want to give an arrow in Q. So every y and x, again my notation is contravariant. For any two objects, x and y, I want a HOM. So, right? It has to be an arrow in Q, so it has a domain and a codomain. And indeed, the HOM from y to x has to be an arrow, it's called contravariant, from x to y, the type of x to the type of y in Q. Okay, so there is a type condition on these HOMs. Now, if I speak of a category, then there must be some kind of multiplication and some kind of unit, but it's the enriched version, enriched over a Quantaloid, so things simplify. Here is composition, it reduces to some kind of transitivity. So the HOM zy is an arrow from type of y to type of z. I can compose with the HOM yx, which is an arrow from type of x to type of y. This has to be smaller, so this composition lives in the sublattice of arrows from type x to type z. It has to be smaller than c, the HOM from z to x. So it's a kind of transitivity. It's the composition law from the enriched point of view, but it reduces to a transitivity because we are working in a post-settled bicategory, locally post-settled bicategory. And the identity law is the following. If you have the HOM in your category from x to x, it's an arrow from the type of x to the type of x, and I can require this to be above the unit arrow. Okay? Now, We'll work out some examples after the break. I'll just want to leave you with the very natural notion of Q functor f between two such Q categories, say C and D. So what do you typically want from a functor? You want it to associate objects to objects, and you want to compare HOMs. That's what a functor does. So if you have this definition and you have a little bit of feeling for this kind of objects, we have an object set, so we're going to ask that the Q functor is a map. I'll also write it as f from the objects of C to the objects of D. But it has to be functorial, so we have to be able to compare HOMs in C, or HOMs from C, and HOMs from D. Such that, well, if I take two objects in C and I look at the HOM, then I can use my mapping and compute fx. I can compute fy. I have two objects in D, so there is a HOM in D. Right? And the natural thing to do is to require this HOM to be smaller than this one. You see, it's a sort of functoriality condition. Now, if I want to compare this arrow with this arrow in a quantaloid, then of course, domain and codomain have to match. What's the domain and what's the codomain? They're given by the types of x and y, the types of fx and fy. So another prior requirement is actually that the type of an element x in C is equal to so it's the type in C of x should be the type in D of fx. So functors have to preserve types, and they should be functorial, so they should compare HOMs in a rather obvious way. Okay? So, of course, we can then prove with these definitions that there is a category which has as objects Q categories, which has as arrows Q functors, which compose just as maps compose, and for which identities are really just identity maps. Okay? So I think I suggest we have the break now, and then after the break we'll see some more examples. Definition of Q categories, Q functors, and I gave you a not very exhaustive, a very small list of examples of quantiles and quantaloids. So we can now find out what it means to be a category or a functor in each of these cases. And as I think many of you have already guessed, some familiar categories will turn up. So a quantile is a one-object quantaloid. So what happens if my quantaloid only has one object? Right? This is a singleton, which means that there can only be one function, so it becomes obsolete. Right? And the type compatibility here becomes a void condition. So for quantiles, things simplify. That's what I want to say. We saw that locales are quantiles, and things simplify even more. And the simplest of all locales is the Boolean algebra with two elements. So I can apply my very general theory to this very, very simple example. So what is the category of categories enriched in the Boolean algebra with two elements viewed as a one-object quantaloid? Right? Well, if you look at the axioms, it says that you have a set C0. For any two elements, you have to assign a value 0 or 1. And you have a transitivity. If the value zy is 1 and the value yx is 1, then the value zx should also be 1. It means that this HOM is actually classifying an order relation. It's precisely saying 1 when z is smaller than y is smaller than x, then also z should be smaller than x. And it should always be the case that x is smaller than x because it's bigger than 1. So what I'm saying is that categories enriched in 2 are precisely ordered sets, or pre-ordered sets, if you wish. And the functors preserve the fact, I'm not finding the right word. If y is smaller than x, then I'm saying that f of y should be smaller than f of x. So it's just monotone functions. The predicate, that's the word. Right? So this is just pre-ordered sets. Now, I don't really like to say, I'll say ordered sets for pre-ordered sets a lot of the time. Okay, there is another very important example. Namely, if I take Lovier's real numbers as quantile, what is going to happen with my definition? Again, it's a quantile, so the whole type thing is obsolete. And we just have to give a set of objects. There's a set of objects. Okay, I'll write it maybe C0. And there is this predicate that gives for any 2 objects a real number. So every Cx or Yx is a real number, a positive real number. Right? I'm going to write this differently. I'm going to write my set as x, and I'm going to write this predicate that associates to any pair a real number as something that looks very much like a distance function. Because transitivity, just mind you, the order is opposite, right? This first transitivity condition, composition is plus, and I have to turn around the order because it's the opposite order in this example, is a triangular inequality. The unit is 0, I have to turn around the order, so self-distance is 0, right? So it's precisely what Lovier called a generalized metric space. So categories enriched in Lovier's real numbers are precisely generalized metric spaces. Generalized in what sense? Well, because they're not symmetric. Distance from x to y can be different from the distance to y to x. It's not separated. So you can have the distance from x to y 0, from y to x 0, but x and y different. Okay, and it's not finite. Distances can be infinite. So it's generalized metric spaces. So Lovier's big example. Okay, now here is, in fact, maybe I should just mention, but without too much detail, more generally, if you take one of those what I call T-norms, so continuous T-norms, I'm not going to re-explain the whole definition, I'm not going to work out the example, but in fuzzy sets, this is what people call fuzzy preorders. There are many, many more examples, but I want to insist on, or come back to, time is running fast, I want to come back to sheaves, or at least pre-sheaves. So, I'm doing it localically. I'm taking my pre-sheaf, or sheaf if you wish, on a locale, and I pretend that there is now a way to compute a category. Now, remember, we wanted to work with these truth values. So if x is over u and y is over v, then we wanted to compute the join of all w's such that x restricted to w is y restricted to w. Okay? It's not very hard to see that there is a transitivity law. You can compute it with suprema, you're computing in a locale, so you can explicitly compute this, but it sort of makes sense because where x equals y and y equals z, if you take the common restriction, there certainly x will equal z, right? So we certainly have this composition law. We fall on our knees, we pray to our gods, and we hope that there is also an identity law, but this cannot be the case. Identity law? This cannot be the case precisely because it's a sheaf. So the very nature of having partial elements, local sections, makes this identity law false. Because look what it would say. To say that the top element of the locale, the biggest element of the locale, is smaller than the place where x equals x, would be to say that, well, x exists on the top level. It really means that x is of level top, right? And it's precisely what we do not want. We want local sections. So we cannot do this. We cannot hope for a sheaf to define an L category. Sheaves are not L categories. We have to be smarter than that. Okay? What does work, though, is the following. I take the same set of objects. Let's see. So I take the same set of objects. I look at this same truth value, but I consider it now to be, or I make the observation that certainly if every W is below U and V and I take a join, then I'm still below U and V. Right? It so happens that if I now look at the split idempotent completion of the locale, then this will be an arrow from the type of y to the type of x if I'm smart enough to write it the right way. So let us compute the split idempotent completion of the locale. It's very simple because every element of the locale is idempotent. Remember, the multiplication is intersection, and u intersect u is always equal to u. So the objects of this split idempotent completion are just any elements of the locale. I told you in a split idempotent completion, we take idempotents as objects, but we take as arrows, we take elements of the quantile, it's just a quantile, we take elements of the quantile which are compatible with domain and codomain, right? So u square is equal to u, v square is equal to v. What does it mean for w to be compatible with its domain and codomain idempotent? Remember the equations, it was something like w composed with u should be equal to w. Composition is intersection because it's in a locale. But it's also the same thing as v composed with w, right? But in a lattice, when do we have that w is equal to the meet of itself and another object? It's just saying that w is smaller than u. And here, this equation in lattice language is just saying that w is smaller than v, and when I'm smaller than u and both u and v, I'm smaller than their inf. So this is really saying that this equality predicate is an arrow in a quantaloid. It's an arrow in the quantaloid obtained by splitting idempotents in L. And it goes from, let's say, u to v, or v to u maybe, to make it coherent with my notations. So it means that I want to think of v as a type of y and u as the type of x. Right? So this is now suggesting the following definition. So I'll write it and let you meditate on this. So this suggests suggests that I can define an LSI category, an LSI category, so not enriched in the locale L, but enriched in the split idempotent completion of the locale, whereas objects I take this coproduct of all local sections of my pre-sheaf. In fact, I'm not even using that it's a sheaf. I'm just using that it's a pre-sheaf for the moment. I assign a type U to an element, a local section X, precisely when X comes from FU. So the type of an element of a local section is where it's defined. Okay? I define the HOM to be precisely this L-valued equality. Because then indeed, with these definitions, then indeed, this goes from the type of X to the type of Y, as we saw. Then indeed, we have that X equals Y and Y equals Z is smaller than X equals Z. So we have the composition law in our enriched category. And we have the unit law. The unit law now says that the identity on the type of X should be smaller than the HOM, right? The HOM, which is the predicate X equals X. But the type of X is where it's defined. So let's say that X is in FU. Then the type of X is U. And the unit on an object, on an idempotent in the idempotent splitting is the idempotent itself. Right? So this makes perfect sense. It just says that where is X equal to itself on its domain of definition. Okay? So the reflexivity problem is solved by splitting idempotents. And this, I think, is the big insight of Bob Walters when he did this first in his paper in the early 80s. Okay. Now, this actually produces, let's say for the moment I'm working with pre-sheaves. This produces actually a functor where a sheaf is mapped to this enriched category. It's functorial in the sense that if you have, I mean, it's functorial in the only sense that it can be functorial, that if you have two of these guys, two pre-sheaves for the moment, just pre-sheaves, and you have a natural transformation between them, then there is an evident way in which you can define a functor. Namely, if X is an object of your first enriched category, then it sits in some FU. It has a type. It's a local section of your pre-sheaf, a local element. So if you have a natural transformation, it certainly has a component at level U. So what can you do? You can take X and map it to the alpha U with the right component of your natural transformation. You will end up in GU, which means that your type is the same. This was a requirement for functors. The type is the same. And you can easily do the exercise where you use the naturality of alpha to verify functoriality of this guy here. Okay? So we actually define the functor from these pre-sheaves to these enriched categories. And again, it's not very difficult to see that this functor is fully faithful. Right? So we're starting to get hopes, high hopes, about connecting enriched categories with, well, perhaps even sheaves. Now the thing is that this functor is absolutely not surjective on objects, or not even essentially surjective on objects. It's absolutely not an equivalence, yet. Okay? So what we will do, what we will try, is to find out how sheaves amongst pre-sheaves correspond with particular categories in a way that this functor becomes an equivalence on those restricted classes of objects. Okay. Let's see. Now, I forgot one little thing, or almost forgot. I talked about involutive quantaloids, and I said that this involution is, say, the most appropriate way of dealing with symmetry or the absence of commutativity. In the absence of commutativity, because it's physically impossible in a quantaloid, if you have an involution, you can sort of recover things. Because L is commutative as quantile, when you split idempotents, you will have an involution. Okay? So it makes sense to define a symmetric Q category. So more generally, on an involutive quantaloid, it makes sense to define remark. If Q is involutive, then say that a Q cat C is symmetric when, okay, so the hom for two elements y and x is an arrow from the type of x to the type of y. If I want to compare it with the hom xy, my problem is that the arrows go in opposite directions. So I cannot write an equality. But the simple thing to do is to require that one is the involute of the other. So that's the way how you can bypass or you can adapt symmetry arguments. Another remark that I want to make, we saw that over the Boolean algebra with two elements, my Q categories were ordered sets, pre-ordered sets. But very often we like ordered sets. That's to say, we want x smaller than y, and y smaller than x implies x equals y. For metric spaces, we want them to be separated. If the distance from x to y is 0 and from y to x is 0, we want x to be equal to y. There is a simple way to formulate this for general Q categories, and it's called, we say then that the Q category is skeletal. Okay? So say that Q category C is skeletal. So I'll give it now as an ad hoc definition, and maybe we'll see later a more general kind of explanation for this definition. So say that the Q category is skeletal if whenever the hom for xy is bigger than the identity, so if for all x and y which have the same type, if this type, so this is an endo arrow on this type, which I call x, if this identity on x is smaller than the hom xy, but this identity on x is also smaller than the hom yx, then we want x to be equal to y. It's not very natural as an axiom. It's something that we do because we want partial orders, because we want separated metrical spaces. But you can always make a quotient of a pre-order and make it a partial order. You can always take a not necessarily separated metric space, take a quotient to separate it. And you can always do this also in the Q-enriched case. So it's really not very important, but it allows me to make a precision here concerning my functor. It actually turns out, if you just make the computations, it's very easy to see that the categories that we get are always symmetric, by definition, right? And they are always skeletal. Easy to see. Okay? Right. Now, we've defined this category cat Q. It has Q categories as objects, Q functors as arrows, and you could try to formulate category theory, whatever that would be. So you can compute, you can study this category as a whole, but we want to study also the objects as categories. And what you typically want to do is maybe have some pre-sheaf construction, maybe have some Yonedo embedding, maybe compute some limits, some co-limits, and so on and so forth. Now, typically to develop category theory, enriched category theory, you need your categories, your functors, but you need a third ingredient. even for ordinary category theory. Typically, that would be natural transformations, and then you would be starting with maybe limits and colimits and so forth. In enriched category theory, and especially in the absence of symmetry, when you work over a bicategory or a non-symmetric monoidal category, it's not so easy to introduce, for example, pre-sheaves, because you will need some covariancy at some point. The problem is that not every enriched category has an opposite. It depends on the base that you're enriching in. So there is another way to introduce or to do category theory, and that's by introducing the necessary third ingredient, namely distributors or profunctors or modules, as people call them. So that will be my next section. I'll introduce a new kind of morphism between Q categories that we will call distributors. I'm obliged to call it distributors because I work in France and Benabou invented them and called them distributors. And then other people call them modules or bimodules or profunctors, and I'm all right with all of these terms, but I will say distributors, okay? So I'll introduce a new type of morphism between Q categories, and it's the interplay between these distributors and the functors that will create my category theory, my theorems, if you wish. So here's the definition. And I'll first, impose it, and then we'll see that we actually already saw it in some sense. So a distributor that I'll write as phi from a category, say A to B. Okay, I'll write it like this. So I'll decorate my arrow to show that it's not a functor, that it's a special thing, a new thing, is given by, well, a collection of arrows. So it looks already a bit like a matrix. So it's somehow a matrix. So it's a function from, so again, I'm writing things contravariantly. So I associate to any two objects, one in A, one in B, I associate an arrow in Q. And again, I have to specify types. I want this to go from the type of A to the type of B. Okay? It's not just this. There has to be some compatibility with the domain and the codomain category. So we have some kind of matrix of arrows in Q that want to be compatible with A and B under the form of the following action inequalities. So whenever you have in B, you have some B prime B, a hom, which you compose, so it's an arrow from the type of B to the type of B prime, which you can compose with such a phi BA. So I'm going from the type of A to the type of B, from the type of B to the type of B prime, I can compose. I could also go straight from A to B prime. Then I want this guy to be smaller than this guy. So somehow you sense that B is acting on phi. That's why people also call it a module. Phi BA after AA prime. So similar story. I have an arrow from type A prime type A composed with an arrow from type A type B. I want this to be smaller than phi BA prime. And that's it. Okay? Distributors compose have identities, have supremum, but actually I don't even need to define this. I just need to remark that we already know distributors. We already know them because if I take a small Quantaloid Q, my Quantaloid will be small to avoid size issues. If I have my small Quantaloid Q, we saw that you can take matrices in Q. It's the plus completion, if you wish. And we also saw that this is a new Quantaloid, right? And we saw that we can split idempotents. Now we can split all idempotents, as we did. We can also split a selection of idempotents, right? We just take a class of idempotents, and instead of, we write the new Quantaloid whose objects are only those idempotents that we like a lot. Okay? Now, if I take this matrix construction and I split monads, so my class of idempotents that I will be splitting are monads. So internal monads. It's the class of arrows, so say f's, for which f square is less than f, which is bigger than an identity. So all endo arrows in a Quantaloid. So I'm reading the Quantaloid as a 2 category, and I'm just formulating what it means to be a monad in a 2 category. If I look at all monads, so that's to say arrows which are bigger than an identity and whose square is smaller than the arrow itself, so there's a sort of composition law and a unit law, I can split monads, right? So what is an object? What is an object in this sum completion monad splitting? An object is a monad, a monadic matrix. So here, an object is, it's a matrix which is a monad. So a matrix is given, an endo matrix is given by a matrix on a set, such that, well, it should satisfy these 2 inequalities. Right? Now, this matrix is, of course, composed or consists of many elements, m, y, x's. Okay, it's a matrix. Matrix composition says that the join of y of m, z, y composed with m, y, x should be smaller than m, z, x. The identity matrix says basically that the Kronecker delta, if you wish, x, x prime, should be smaller than m, x prime, x. Right? But this simplifies. When is a join of things smaller than another thing? I can forget the join. It's just the case when every term is smaller. When is a Kronecker delta smaller than a given element? Well, 0 is smaller than everything, so that's not requiring anything at all. It reduces to saying that 1 on the type of x is smaller than the value of the matrix in xx. I've written exactly the definition of a Q category. So a Q category is also precisely a matrix which is a monad. Right? Now, in this universal construction, there are also arrows, right? So what is an arrow in this big Quantaloid? It's giving, well, between 2 monads, so between an m and an n, I have to give a m, n, I don't know, p, which is compatible, right? So we said such that p after m is p is n after p. Now you recognize here that in fact, these equalities, they actually are equivalent to the inequalities up there. Not difficult to see. So what it is really saying is that this P is a bunch of arrows such that, so it's completely equivalent, such that P yx m x prime is smaller than P yx prime, and the other one n y prime y after P yx is smaller than P y prime x. And you recognize precisely the distributor axioms. So in other words, I gave you an explicit definition of distributors, easy to compute, easy to verify examples, but it's actually coming out of a universal construction which underlies its importance, if you wish. Right? If something arises universally, it must be important. A very important consequence is that without any further computation, we can assert that categories and distributors form a quantaloid. They compose, they have local suprema, it means that we have residuation and all that. Right? So corollary, dist, which I'll call dist Q, which is Q categories and Q distributors, which is actually literally the same thing as matrices over Q and then splitting monads, is a quantaloid. So there is, for the moment at least, Q categories and functors, which is a mere category. Q categories and distributors, which by universality is a quantaloid. It's much richer. It's a much richer context. You can do computations which involve composition, of course. In a category you can do this too. But here we can do computations which involve two cells, because there are two cells. It's ordered, locally ordered. We can do computations which involve residuation. And all these things we cannot do with just Q categories and Q functors, because it's just a category. Right? So we can do interesting stuff, but for the moment it lacks two structure. It lacks two cells. Now luckily for us, these, and it's a very general principle, and again I'm explaining very general things but apply to a simple context. Luckily for us, there is a very nice comparison between functors and distributors. Namely, every functor determines an adjoint pair of distributors. And that's somehow the point where we can start to do interesting things. So I'll try to explain this. Let's see. Yeah. So I probably should first say, or at least compute a very simple example, or say what it means in a simple example. When your quantile is just a Boolean algebra with two elements, we saw that Q categories are pre-ordered sets. We saw that Q functors are order-preserving morphisms. What's a distributor? Okay? So if I take a pre-ordered set A, I take a pre-ordered set B, what is a distributor? So think of these as categories, meaning that you think of the HOM, x, y, as the truth value for x being smaller than y. What do my, I raised my conditions. What do my action inequalities say? They say that, for example, I'll change my notation, sorry. So BA and AA prime should be smaller than phi BA prime. And my other action inequality was B prime B. Composition is intersection. It's Boolean algebra, it's a locale. BA smaller than phi B prime A. So let's read this. This distributor is actually a bunch of truth values. So it's either 1 or 0. It's either true or false. So this distributor classifies a subobject of the product. Right? It's either true or false that B something A. But whenever it's true, so whenever BA has value phi value 1, and A is smaller than A prime, then it should also be the case that B A prime is in phi. Right? So I'm thinking of phi as the characteristic function of a subset. Right? That's basically what I'm doing. So when a couple BA is in phi and A happens to be smaller than A prime, then also BA prime should be in phi. If B prime is smaller than B and BA is in phi, then B prime A should be in phi. So it's actually a subset of B times A, which is downclosed in B and upclosed in A. Meaning that whenever BA is in phi, B prime is smaller than B and A is smaller than A prime, then B prime, A prime should also be in phi. So it's a relation which is compatible with the orders in a particular way. It's downclosed and it's upclosed in the domain and downclosed in the codomain. Right? So sometimes this has been called ideal relations. Maybe it's not a very good name, but anyway. There is another famous example, and it already hints at something that we will be developing. Maybe not today, but at least tomorrow. There's another example where I work with famous example by Lovir with a quantile which is 0 infinite with its opposite order. So remember that categories were generalized metric spaces. Okay? I take such a generalized metric space, but you can easily take just a metric space. So remember what happened. We said that as a category, X is its object set, and the distance function gives the hom. Okay? Now look at the following. It's maybe a little bit more complicated. I take a sequence in the space. I take a sequence in the metric space. I claim now that I can make a distributor which goes from a singleton metric space to my metric space so that I identify with the category C. I claim that I can compute an interesting distributor associated to a sequence. What is this distributor going to do? So it takes values in a singleton and an element of C. But it's always the same singleton, it just doesn't play a large role. So this is really a function from C0 times singleton to 0 infinite. Taking a product with a singleton is not very meaningful, so I will just forget about it. So in fact, to specify a distributor from a singleton space, so with 0 distance, and my metric space viewed as a category, is just specifying a function which satisfies the action inequalities from my metric space, the elements of my metric space, to the real numbers, positive real numbers. So here's what I propose as a definition. So for every x, I will compute, so I have to make sure that I write it the right way. So I compute the distance from x to a term of my sequence from a certain point on. So the tail of the sequence, and I do this for all possible tails. Right? So I'm writing here a function that computes the distance between an arbitrary point of my metric space to the tail of my sequence. right? Now my distance function is not necessarily symmetric, I told you. So there's actually sort of symmetrized version. I can also define a similar kind of function that will compute the distance, but now the other way around. Of course, if I'm working over a real metric space, a symmetric metric space, these are the same thing. But I will compute the distance from between x and the tail of my sequence. Right? Turns out that this is another distributor. Now, what Lovere famously showed in his beautiful paper from early 70s is that this guy is Cauchy if and only if these guys are adjoint. All right, so this is a famous result which actually justifies, if it was still necessary, the use of distributors and the importance of distributors in the context of enriched categories. And so here in this very famous example, Cauchiness for a sequence turns out to be completely characterized by adjointness of distributors. And what's more, every adjoint pair of distributors comes from an equivalence class of Cauchy sequences. I think we have a specialist here in the room on this topic. Okay. So I'd like to, can I take 2 more minutes to finish? Because I'd like to just leave you with the comparison between functors and distributors in case you want to verify a couple of things. Because I told you we now have these categories, we have these functors, we have these distributors. And there is a very nice way to produce with every functor an adjoint pair of distributors. So that's the following proposition. When you have a Q functor between any two Q categories, so functor, a Q functor between Q categories, then there is an adjoint pair of distributors represented by this functor. So this is how it goes. I have to define, or I claim that I will define a distributor, I'll call it F lower star and F upper star. And I claim that these are adjoint. So adjoint in the Quantaloid means adjoint as in any old 2 category, right? So it means that composing one way you are bigger than the unit and composing the other way you're smaller than the unit. Everything is locally ordered, so there are no coherence issues. So how should I define this F lower star? F lower star is the distributor represented by F. So its values in BA, right? So if I define a distributor from A to B, I should give its values in elements in couples BA, written contravariantly. It's just going to be the value, the hom in B, when I compare B and F of A. So it's just the hom in B between B and FA. The other way around, well, you can now almost guess. If I have to invent a distributor which goes from B to A, I have to give its values in couples AB, and I will just take the hom in B between FA and B. Okay? This always works, this always produces distributors, and this always produces an adjoint pair. So to be really precise, meaning that if I do first F star and then F lower star, F upper star, then I am bigger than the identity on A, which is A itself. And if I do first F upper star and then F lower star, then I should be smaller than the identity on B, which is B itself. So for any functor, we can make this computation. It's easy to verify because essentially we're just using multiplication in B to use and functoriality to check the action inequalities. It's easy to check that we have 2 distributors, and it's easy to check that they are adjoint. So what's the good thing? That this construction is functorial. So it turns out that even have a functor which goes from Q categories and Q functors to Q categories and Q distributors. So there is an inclusion, if you wish, from functors to distributors, whereby you send, if you want it to be covariant, you send f to f lower star. Okay. And it's even better than just this functor, because I remarked that f lower star is always a left adjoint. Now, it's common to call a left adjoint a map in a 2 category. So we can even say that we have a comparison functor between Q categories and functors and Q categories and left adjoint distributors. Okay. Now, this is a Quantaloid. Distributors is a Quantaloid. Once you take maps, you destroy, perhaps, probably, the quantaloidal aspects, right? Because the join of maps is not necessarily a map. Join of left adjoints is not necessarily left adjoint. So this is a comparison between 2 categories. Now, the thing is that distributors form a Quantaloid, so a 2 category, whereas this guy was only a category. But by embedding a category in a 2 category, you can sort of pull back the extra structure. So using this, we can define a local order on the categories. We can now define 2 cells. We can now define natural transformations by transporting structure. So we define f to be smaller than g, right? So I define a 2 cell. F is smaller than g, which I didn't have before, precisely when, as distributors, where I do have 2 cells, it is the case. So there is 2 structure available that I transport. The thing is that this is precisely equivalent to saying that for all A in A, the type of A is smaller than the homin B of FA GA, sorry. Okay? So it's precisely saying that there is sort of pointwise order. And so you can easily understand in the example of, for example, preordered sets, that not only do we have preordered sets and monotone maps, but also the local order of them. Except that now, in this very general scheme, it is inherited from the distributors. Okay, so we have this functor. We will use this functor as starting point in the next lecture to discuss actually when it is the case that locally we have equivalences. This will be the concept of Cauchy completion or Cauchy completeness of a category, and then I'll try to indicate how we precisely recover the sheaf condition in the case of the category associated to a sheaf or to a pre-sheaf. Thank you.